So welcome to part 2 of our lecture on hydrogen, and this will be the main body of the lecture, the longest video, because now we're going to be looking at hydrides, and these are the compounds that hydrogen makes with most other things in the periodic table. So hydrogen can form what's called a binary compound, so a compound that consists of just two elements with pretty much everything else on the periodic table. Not everything, so you can see at the bottom of some of the groups here, the hydrides aren't known. But yeah, with most things, and as I said, these are called hydrides. But the properties of these differ tremendously throughout the periodic table. And the main thing that governs this is the electronegativity of hydrogen, and that is 2.2. So we'll keep coming back to this periodic table that's taken from the Chemistry Cube textbook. And you can see already that there are many different colours corresponding to many different types of hydrides. So over on the left-hand side with the alkali and alkali earth metals, group 1 and 2, it forms ionic hydrides, and these generally solid. With beryllium and the top of group 13, we've got electron deficient ones. Here we've got electron precise covalent hydrides and electron rich covalent hydrides here. And depending on the electron deficiency or preciseness or electron richness, we also see differences in the chemistry. So we'll go through group by group and see what the differences are. But first we should look at how the bonding is affected by the electronegativity. So we've got down here a scale of covalent bonding to ionic bonding. We've got an example we looked at in ionic structures, the rock salt, which is purely ionic. Covalent would be the H2. The electrons are shared equally. And then we've got something in the middle of covalent and ionic bonding with the hydrides, where it's unequally shared. So there's like a partial charge, a dipole, we call it. So for the left-hand side, we call them ionic hydrides. They're not strictly as far as NaCl. They are still dipoles because it's just quite a big difference in electronegativity. But when it makes hydrides with group 1 and 2, hydrogen is the more electronegative. So it's actually got the partial minus charge on the hydrogen. Whereas if we looked at the HF example down here, the partial minus charge is on the fluorine, or it would be on the oxygen in the case of water, because they're more electronegative. And we'll come to it again later on, but you can see beryllium's actually got quite a high electronegativity compared to the rest of group 1 and 2. So that acts as a bit of a strange case. So when hydrogen forms these binary hydrides, you can have two different types of hydrides depending on the oxidation state of the hydrogen atom. So if it forms a binary compound with a more electropositive element, so this will generally be the elements on the left hand side, the S block, it's called a hydridic hydride, and this is because the hydrogen is in the -1 oxidation state. Whereas if it forms it with a more electronegative element, so the ones on the right hand side, like the halogens, oxygen, nitrogen, things like that, it's then called a protic hydride, or protic hydrogen. And this is because it's in the oxidation state +1. Now I've put a help sheet online for calculation oxidation states. I think it's something you should have done introduction to chemistry. If it's not, let me know. But as I say, I've put a worksheet on Learn Central, Blackboard, to take you through how to calculate what the oxidation state is, and also see in reactions how they change. So whether a hydride is hydridic or protic also is reflected in the naming of the compound. So on the left hand side here in group 1 and 2, laser pen, group 1 and 2, and also a bit of a group 13 as well, we see it's the metal followed by hydride. And this is then if they're hydridic compounds, so the hydrogen is in the -1 oxidation state. And it also kind of follows the naming convention of the cation being first and then the anion second, which we'll also see on the right hand side of the periodic table. Even though they're not strictly a full cation and anion, it's more of a delta plus, delta minus. You've then got the lithium first, which is the positive dipole, and the hydride second, which is the negative. So this is for the hydridic hydrides. And then this side we've got the protic ones. In the middle, the naming is a bit less conventional. They end in ane for group 14, For group 15, they generally end in "ine", although yeah, ammonia we've got a sort of traditional name for. And then also water is a bucking convention. Then when we get far to group 16 and 17, then it follows the hydrogen fluoride, chloride, sulfide. And this again is going back to the positive charge first. So hydrogen in this case is the +1 oxidation state, and the more electronegative, sort of the delta minus, being the second half of the name. So the covalent hydrides, and these are the ones that are formed from p block elements and hydrogen and beryllium and hydrogen, can have three different types of covalent hydrides. You've got electron precise compounds, which have all of the electrons of the central atom involved. So this would essentially be like the octet rule being filled as well when we were looking at Lewis structures. And this is all group 14 hydrides, so things like carbon, which makes methane, and silicon that makes silane. They're electron precise covalent compounds. We can also have electron deficient covalent compounds, and these are slightly rarer. They are things like borane, so a combination of boron and hydrogen, and also beryllium from the S block that I was talking about. And then we've got electron-rich compounds, so not all of the electrons on the central atom are involved in bonding. And there are quite a few of these. Water falls into this, ammonia, the halogens, so yeah, group 15 to 17 hydrides. So these have lone pairs present, and this will affect their chemistry quite a lot, which we'll see in this lecture, but also we'll be looking at how they affect trends in the next lecture as well, next video even. And to explain what an electron deficient compound is, and especially this 3-center 2-electron bond, which sounds a bit confusing, there's a diagram down here, and also a really good video, again taken from the Chemistry Cubed YouTube channel, the author explaining what a 3-center 2-electron bond is. But it's essentially involving both the borons. So if we take the example of borane here, so it's B2H6, well, they've gone for the anion here. Involves the two borons and also a bridging hydrogen. And between these three atoms, so 3 centers, there's sort of one big bond. Sometimes it's referred to as a banana bond that has 2 electrons in it. So as opposed to a normal bond that's just 2-center 2 electrons, so a boron and a hydrogen with 2 electrons between them. This is 3-center because it's 2 borons and a hydrogen all sharing 2 electrons. And you can explain how it works with a combination of the valence bond theory that we were looking at in the revision lecture, so the sp2, sp3 hybridization schemes, and also combining that with molecular orbital theory to see how you can take 2 sp3 hybridized orbitals. So these will be, these are sp3 hybridized orbitals around the boron. So we take 2 of the sp3 hybridized orbitals, one from each boron, and the 1s orbital of hydrogen, and they end up forming 3 molecular orbitals, one that's sigma bonding, and this will be through an in-phase combination of everything. So 2 sp3 orbitals, let me try and draw it. There we go. So we've got an sp3, the 1s of hydrogen, and the sp3 of the other boron. If they're all in phase, you get this sigma bonding orbital. And that's because there's a nice overlap of everything. It's continuous phase. You get a banana bond, and that's why it's called a banana bond, because it makes this sort of banana-shaped molecular orbital. Then, if say the 2 borons were in phase, but the hydrogen was out of phase, you'd get an antibonding orbital, which is shown at the top here, because the hydrogen is out of phase with the 2 sp3 hybridized ones. And then, if the 2 borons, so if we put a plus and minus here, if these were out of phase, you'd end up getting a non-bonding interaction, because no matter if the hydrogen was, say, positive phase or negative, the symmetry is wrong. It would always cancel out the bonding and anti-bonding, and that's how we end up with this non-bonding orbital as well. So that's a bit about, the electron deficient bonding. I'm sure we'll come back to that again later. So let's work our way through all the groups and just see, how the hydrides behave. So we're going to start with the S block. which is on the left-hand side, and these are the ionic hydrides. So group 1 hydrides are formed by a combination of the elements at high temperature. So if you just heat up sodium and hydrogen, you'll end up with sodium hydride. They're largely ionic, and this goes back to what I was saying earlier. They're not truly ionic like something like sodium chloride would be, but there is a large difference in dipole where the hydrogen has a large delta minus charge, and the alkali earth or alkali, all of them, alkali metals and alkali earth metals, have a delta plus. They're colourless, high melting solids. They have the rock salt structure, if you remember that from the last lecture, and they're strongly basic. And the same with group 2, and this is why they're called alkaline and alkaline earth metals. They react with water to give an alkaline solution. And it's very similar with group 2. Their hydrides mainly crystalline, they're ionic, and they react with water to give alkaline solutions. The one exception to this is the orange highlighted one here, which is beryllium hydride, and we'll look at that on the next slide. So one big difference is that beryllium hydride is stable in water. It doesn't rapidly react to form an alkaline solution. And also it has a 3D covalent polymeric structure. So almost like the covalent networks we were looking at in the last lecture as opposed to the ionic structures. And these have the 3-center 2-electron bonds we were talking about. So these green centers are the beryllium centers, and all these grey atoms are hydrogens. And the bonding around a beryllium center is generally tetrahedral. And then with all of these bridging hydrogens, it's this 3-center 2-electron bond. So you get these large covalent structures, but they're electron deficient because 2 electrons are shared across 3 centers in each of the bond. There is a good use for S-block hydrides, and these are as hydrogen storage materials. So if you remember back to, I think it was the last slide of the first video, I was talking about the hydrogen economy and how hydrogen can be used as a fuel because it's very energy dense when you think of it in mass. But when you look at energy density on a volume scale, one of the big problems is that it's very hard to get hydrogen gas into a vehicle in a useful amount. So metal hydrides can be used as hydrogen storage compounds. So I've got the example here of magnesium hydride. So magnesium can absorb 7.7% of its own mass in hydrogen, which is quite a lot. So you can put the metal hydride in the car, say, as a storage site, and then upon heating, the hydrogen's released from the magnesium hydride and can be supplied as gas. So it's just a very good way of storing a lot of hydrogen in a much smaller space. However, the issue with this is lifetime. So impurities in the gas are irreversibly absorbed. So if you add like CO2 in the gas or CO, they'll irreversibly bond into the structure, and your hydrogen storage capacity won't stay at 7.7% for long. It will go down. So now we'll focus on the P-block hydrides. We'll go across group by group and see the bonding here. So if we start with group 13, you can see at the top they're either the electron deficient ones, which is exactly how we were describing the bonding in beryllium hydride as well. So they've got a lot of these 3-center 2-electron bonds. And down the bottom of the group with indium and thallium, they're not actually known. These hydrides don't necessarily exist. We've got the simplest borane here, which is what I was using to explain the 3-center 2-electron bond. So this is a 3-center 2-electron bond, and these are just normal covalent bonds. But it doesn't just have to be B2H6. You can get a large number of them, with either BNHM+4 or HM+6, like decaborane. So this is shown here, and these are large cage-like structures. The other hydrides, aluminium hydride and gallium, aren't as stable or as diverse, so you won't get sort of decagalane, I guess they try and call it, but they're not as stable, so you can't get those. And the decomposition temperature decreases down a group as they become more reactive. And you'll see this trend for all of the groups in the periodic table. And this is related to a decrease in the hydride bond enthalpy. Group 14 is the group with electron precise hydrides, which is why we've got the yellow ones shown here from that periodic table. The lead hydride is plumbane is theoretical, that's not really made. And the main interesting chemistry here is with carbon, because it forms an unlimited number of hydrides, which is the basis of organic chemistry, which you're going to spend half a semester studying. So that's the most important one. With silicon, the silanes, they can't make an unlimited number of hydrides like carbon, but you can get quite large hydride chains. So you could also get Si2H6, things like this. They can grow only up to, I think it's 8 or 10 silicon chains. And then, like most things, the hydrides become less stable as you descend the group. And we'll see why later in the next video, I think, actually. Group 15, demonstrated as blue, and this is because they're electron-rich covalent hydrides, and going across they always will be. So these are the first with lone pairs, and that affects their chemistry somewhat. So we've talked about ammonia before and how it's the main product that we make, the main hydrogen-containing compound we make on Earth. Also, you can make larger ones. There's N2H4 hydrazine, which is very exciting, very toxic, but it can be mixed with an oxidant such as N2O4, which makes an incredibly powerful reaction, and that's used as rocket fuel. So it's a very high energy density. And an example can be seen here on YouTube actually. This is only like a 20-second video. It's not with N2H4, I think it's with permanganate, but another oxidizing agent. And it's just the minute hydrazine hits an oxidizing agent, it's violently oxidized and immediately ignites. So these are also called hypergolic fuels, because you don't need any ignition source, any heat at all. You just mix the two liquids and they will create fire. So we've got phosphine and arsine shown here. These also form the X2H4, such as hydrazine. Also high energy density. And again, the hydrides will become less stable as we go down the group. It's the last slide for this video. The last hydrides we'll be looking at are group 16 and 17, because as usual, group 18 doesn't react with anything, so we don't have sort of neon hydrides or anything. So looking at group 16, we have water. So this is the hydride we know we're made up of, the world is covered in, and is key to our existence. So as this is, as I was saying, key to our existence, the others are highly toxic. So this is not a trend that the group 16 hydrides are beneficial to our health. The other thing is that water is the only liquid in the hydrides of this group. All the rest are gases. And this is again because the stability decreases down the group. And finally, we have the hydrogen halides. So if you remember in the first video, I said that the halogens are the only things that will react in the gas phase with hydrogen. So just a direct reaction of hydrogen gas and halogen gas will make the hydrogen halides. They're more acidic as the group is descended, and this is again because the bond is weakened as we go down the group. They're less stable, and then because they're giving away a H+ as they go down, they become more acidic. So hydrogen chloride is the one we quite often use in the lab for an acid. Hydrogen bromide is even more acidic. Hydrogen fluoride, or HF, even though it's not very acidic, is used in the lab a fair bit, especially industrially. It's used in glass etching because it can literally dissolve glass, but it's probably one of the most toxic things we use in the lab. So I'll give you a little bit of a background on my project one day in a discussion session probably, but my project is essentially looking at the zeolites for degrading chemical weapons, and we don't really use chemical weapons like VX in the lab because they are more dangerous, but we use chemical weapon simulants that are almost as dangerous, and hydrogen fluoride is really on the same safety level as these chemical weapon simulants. You've got to have two people in the lab using it, so if it spills or anything, you've got immediate health and safety. And the fluoride ion gets in your body and really just strips all the calcium out of you, and most other ions actually, which isn't very nice for you. So that's very dangerous. So now we've got a nice overview of what the hydrides of the periodic table look like, and some real life examples, and some that you really want and some that you really don't want. And in the next video, we'll look at the reasons behind some of these trends, such as the instability going down the group.